This video is a mega review of the chemistry reference tables for the Regents exam. We haven't had a June Regents exam since 2019, folks. This is 2022. This is going to be good. I broke up all the different tables, and the last three Regents exams put the questions by the table so we can review together. Get a pen and pencil ready, your calculators, and let's get going. Here it is. These are January 2020, August 2019, and June 2019 Regents exams. Reference Table A, there are a few questions I listed here. A link is going to be in the description below of where you can find a copy of this packet. You can do the questions yourself if you want, and then go ahead and listen to the video. You can just listen along with me. The key is that you remember you have these reference tables. You can go ahead and you need to find information a lot of times on the reference tables to go ahead and process information. With that, let's get started. With number one here, we're looking at the greatest distance between molecules at STP. If you had forgotten, reference table A shows you STP is standard temperature and pressure. Standard pressure, you're given 2 units, and standard temperature, 2 units. So this comes in handy also if you need to convert between one unit and another. In this case, that's not what they were asking in question 1. They were just asking you which phase are the particles that make up that substance going to be furthest apart. And of course, that is your gas phase, which is nitrogen, which is answer number 1. Okay, the next two questions here, you see we have a data table. They're talking about 5 substances at standard pressure, and you're asked about identify the substance in this table that is a liquid at STP. Now, you might have memorized that you have 2 liquids of the elements on the periodic table. One of them is bromine, one of them is mercury. Bromine is here, but we want to compare it to standard temperature, which is 273 K. Let's take a look. The answer is going to be bromine, but let's just make sure. So standard temperature is 273. Look at HCl. If you take a look at these values and you make a number line, 273 is going to be higher, right, than the melting point and boiling point. That tells you for HCl, if it's a 273, you have hydrogen chloride in the gas phase. Next one, nitrogen monoxide. Again, 273 is higher than the 109 or 121. So it's gone through the melting phase and then gone through boiling, right, from liquid to a gas. Then we get to fluorine, same thing once again. Fluorine, or F2, is going to be a gas at 273. Then all of a sudden we get to bromine. 273 is between the melting point, which means it went from a solid to a liquid, and the boiling point, going from a liquid to a gas. That's why it's our answer. Finally, for iodine, 273 is all the way here if it was on a number line. So iodine is a solid at standard temperature. Let's move on. Number 3, convert the original air pressure in the cabin of a submarine to atmospheres. Now, this question was part of a multi-type question, and I put here the value that we have to go ahead and we have to convert. 160 kilopascals to atmospheres. You don't have to memorize the conversion. However, if you don't know where to look, you're going to run into a problem. So let's take a look at reference table A. All right, here on reference table A, under standard pressure, 101.3 kilopascals, is 1 atm. I need that information now and figure out 116 kilopascals, how many atms that is. Depending on your teacher might have had you set up proportions. You might have had a teacher that does conversion factors. Either way, you're going to get to the answer. So let's set this up then. Okay, so here's the setup to convert. 101.3 kilopascals over 1 atm in proportion with now 116 kilopascals over X. Yes, you just cross multiply and divide, and you get the answer. You could also use this here fraction as a conversion factor. Let me show you that. As you can see, two different ways for exactly the same answer. I rounded to 3 significant figures because the question or the number given was 3 sig figs, or 1.15 ATM. You don't have to worry about units in this case. You're only doing the conversion, and you don't have to memorize the conversion between kilopascals and ATMs. You just have to look at reference table A. All right, so let's check out some questions that relate to table B. Actually, it's going to relate to table B and some equations on table T. Table T, that's the last page of your reference tables, has, as it says here, important formulas and equations. And if I scroll down, you're going to see these 3 heat equations. The constants for C, HF, and HV, that's all part of table B. Let's go back. All right, and let's take a look. In question 1, they're talking about heat released by 1 gram of liquid water at 0 degrees when it changes from 1 gram of ice at 0. Now, you're having a phase change here at a specific temperature, but we're dealing with melting, and melting is fusion. 334 joules per gram of ice, and there's my answer. It is choice 3. Yes, they give you the temperature, but this isn't a delta T. Remember that temperature is constant at a phase change. So the answer is choice 3. Let me scroll down a little bit. Let's look at question 2. What is the amount of heat absorbed when the temperature of 75 grams of water increases from 20 to 35 degrees Celsius? Now there's going to be a delta T. This is Q is equal to MC delta T. And let's go ahead and plug in the values. And because it's water, we're going to use the specific heat capacity for water as a liquid, this 4.18. Okay, so here you see we got 75 grams of water, 4.18, that's our constant, delta T, 35 minus 20. Do absolute value here, don't worry about the sign for Q. I haven't seen a Regents question yet where they ask you about the sign, whether it would be positive or negative. We're looking for the magnitude of the number. When you go ahead and plug it in the calculator and you round it to 2 sig figs, the answer here will be choice 2. All right, we're moving on down to this next group here. In this example, we have a 100-gram sample of liquid water heated from 20 to 50 degrees. There's enough potassium chlorate is dissolved in the sample of water at 50 degrees Celsius to form a saturated solution. Notice they're guiding you here to some of the reference tables. That this is not always the case, but if you're told where to go, you follow it. Let's check it out. Okay, question 3, we're using table B. That's the constants for water. Determine how much heat absorbed by the water when the water is heated from 20 to 50. We have the Q is equal to MC delta T. Do the setup again. Calculate the answer. Notice now you're going to just write the answer in the answer booklet. All right. I set up the problem. Q is equal to MC delta T. M is 100-gram sample. My C, that's from reference table B, 4.18. And my delta T, it looks like it's 38, but it's actually 50 minus 20, which is 30. You go ahead and multiply those together, and you're going to get 12, 5, 4, 0. And of course, this is in joules. Now, it didn't specify units, didn't even talk about sig figs, so you can just leave it just like you get it off of the calculator, and I would recommend that. If the question specifically asks for significant figures, then you're going to follow the rules there. Now, we've just had, of the 3 Regencies, definitely a calculation with either Q is equal to MC delta T and then one with Q is equal to MHF. You will see another calorimetry question on the Regents exam. They show up at least once in exam. All right, the other two questions, number 4 has to do with table H and number 5, table G, but I didn't want to cut them apart. Let's just tackle those here. So in number 4, we're going to go to table H, and we're going to determine the vapor pressure of water, let's see, at its final temp. The final temp is 50 degrees Celsius. Let's go. Reference table H is your vapor pressure for 4 liquids: propanone, ethanol, water, and ethanoic acid. We're dealing with 50 degrees Celsius, and we're dealing with water. What you're going to want to do, especially on your reference tables for the test, mark them up. We're dealing with water. We're dealing with 50. We're going to go ahead up to where crosses the line and then over. Now, it's hard for me to do on this computer, and I apologize for my lousy writing, but it turns out we're dealing with just over the first box on vapor pressure, which is in kPa, and you'll notice it's 10 kPa per box, but we're slightly higher. So I would recommend maybe you're going to estimate, and on the answer key, the teachers will get a range, but let's say you say 12 kPa. So that's how you're going to answer the question here. At 50 degrees Celsius, 12 kPa for the vapor pressure. Somebody else says 11. I'm sure you would get credit either way, because when things are not crossing the line perfectly, we get a range when we do the answer keys. That then is our answer for 4, 12 kPa. Let's run to 5. Now we're going to table G. It says determine the mass of the potassium chlorate that must dissolve to make a saturated solution in 100 grams of water at 50 degrees Celsius. Well, let's do that. Table G is our solubility curves. That's what will fit in 100 grams of water. That's on the y-axis here for a certain solute. And the solutes, of course, these lines are different because different solutes are going to have different properties. Now, we were dealing with potassium chlorate. You have to find the potassium chlorate line, all right, and use the little arrow. And we're at 50 degrees. So once again, it is not crossing specifically at the lines here. I'm going to go up, maybe not, hold on. All right, I'm going to go up and then I'm going to go over. It's crossing slightly above 20 grams in 100 grams of water. Again, I would guesstimate either 21 or 22 grams in 100 grams of water for potassium chlorate at 50 degrees for your answer. All right, we're moving on to tables C and tables D. And you'll notice I go right to reference table E. There aren't specific questions that I could find in the past 3 Regencies where you had to go and look something up. The selected prefixes for the metric system, very rarely have I seen a metric conversion on the Chem Regents. In fact, I don't think I've ever seen one. So there's nothing to go over here. And as far as table D, these are symbols and the names and what they represent. If you ever get yourself confused, should you take a look here? Absolutely. Will you take a look here? I'm going to say probably not. All right, I can show you one though here at the bottom of table D. Atomic mass unit in New York State sometimes refers to that as U. Personally, in my classes, we've always used AMU. So you can use those interchangeably. All right, let's keep moving. We're going to go to reference table E. Reference table E are your polyatomic ions. These are clusters of atoms that have a charge. And of course, we use these a lot with naming and writing formulas. And then when you have solutions, they'll break apart, but the polyatomic ion would stay together. Along with that, we have the solubility guidelines for aqueous solutions. These are for our salts in water, and this is now qualitative. It doesn't tell us how much will dissolve. It just tells us whether or not a compound that contains one or both ions that are listed in the table, whether or not will dissolve in water or it won't. Do I put it in water and it looks, or it not looks, but it disappears, or I put it in water and it falls to the bottom? If it disappears, it's dissolving in the water and soluble. If it falls to the bottom, we say it's insoluble. This table is really annoying to read. Let me just go back up for a minute. If you're asked about writing a compound formula or naming a compound, remember that the charges here need to balance out with whatever the polyatomic ion would be bonding with. You never change a polyatomic ion name either. It doesn't change, the ending doesn't change, anything like that. Here for our solubility guidelines, this column is soluble. The exceptions means that these are insoluble. Then you have a column of insoluble, and then your exceptions are soluble. So the two outside columns are for compounds that contain one or both of these ions that make it soluble, and then the inside columns are for things that don't dissolve in water. Now, you don't have to have both pieces. As long as you have, for example, let's say you had sodium phosphate. Phosphate is listed as insoluble. Sodium, of course, is soluble. Sodium phosphate, in fact, anytime you have a sodium symbol written in a compound formula, you have a compound that will dissolve in water. All right, so if it's soluble, you have to only have one of the two. All right, let's keep going here. Oops. Sorry. All right, so here's a couple of questions that have to do with those two tables. In question 1 here, the chemical formula for sodium oxalate. Now, you don't have an IDE ending. Typically, an IDE ending is for your binary compound, your metal and your nonmetal. An ATE ending means you have, of course, a polyatomic. Depending on the charge on the polyatomic, in other words, how many electrons it needs, we're going to have possibly some sort of subscripts. Sodium, on the other hand, is a group 1 metal. It always gives up one electron, its valence electron. So let's take a look at the polyatomic ion table. All right, you have your sodium, which is Na, which gives away the one valence electron, that's Na+. Here is oxalate. For a second, I couldn't find it before I turned the video back on. That's C2O4 with a 2 minus or a -2. The charges need to be balanced. In other words, the electrons lost by sodium have to be equal to the electrons gained, in this case, by the oxalate. Since oxalate needs 2 electrons, you need 2 sodiums. Now, your teacher probably talked to you about crisscrossing the values along with the charges. And that's so when I add up electrons lost and electrons gained in a compound, it has to equal 0 because compounds are electrically neutral. So the formula should be Na2C2O4. Now, armed with that information, go ahead back to the question, play the matching game, and you're going to have your answer. All right, so in question 1 here, having to do reference tables E and F, sure enough, it is answer number 4. For question 2, the chemical name of the compound NH4SCN. Well, you definitely have a lot of elements here. The only group that I could see possibly a student getting confused would be if it's an organic compound. But typically organic compounds always have carbons and hydrogens. Every once in a while, nitrogens and sulfurs. But this is for 2 polyatomic ions that are bonded together. You want to go to reference table E and you just want to play the matching game. Remember, I already told you, you are not going to change the endings of anything. So you just need to find the 2 polys that are represented here. All right, I'm showing with the red line the breakup between the ammonium and the thiocyanate. Literally, those two words just go together. Ammonium thiocyanate, done. Just finishing up the question for number 2 here, that would be choice 1. Please do not get creative and make up your own name. Look at the reference tables. Look at reference table E. It's all there. You just have to look. Let's keep going. All right. In these 2 questions, they refer here to the decomposition of KClO3 and this lab data. While question 4 isn't related to reference tables E and F, I'm leaving it in because both of these questions were given together on one of the old Regents exams. All right, so for question 3, write the chemical name for the compound that decomposes. Well, the compound that decomposed was the KClO3, which you can get from the equation, and you can also get that right from here, right? That's our starting material. Well, K is potassium. Now, again, don't get creative on me. KClO3, you want to play the matching game and find it on reference table E. When you do that, you're going to find the polyatomic ion name is chlorate. So the answer here for number 3 is potassium chlorate. There's no excuse. You do not need to misspell potassium either. All of the elements, the symbols, and the correct spelling you can find on reference table S. Let's move down to number 4. It says, based on the lab data, show a numerical setup for determining the number of moles of oxygen produced using a gram formula mass of 32 for O2. Well, once again, let's go to reference table T and find the equation. Okay, here it is, reference table T, and sure enough, the second calculation down, number of moles is equal to mass over gram formula mass. Let's go back and use it in the problem. All right, numerical setup. All that means is you are going to plug the numbers into the equation. Now we're looking for moles. The gram formula mass is given as 32. That goes in the bottom of the fraction, and I need the mass of the oxygen. Let's take a look. Well, guess what? Look at this. You didn't even have to calculate anything. You're given the mass of the O2 here is listed as 0.8 grams. That 0.80 goes right here, and you're done. You don't even have to calculate the answer because you're asked for numerical setup. All right, let's keep going. Okay, again, we have some information here of about a bottle of water and a 500-gram sample and ions that were detected and their masses given in that water. Question 5, based on reference table F, write the formula of the ion in the bottled water table that would form the least soluble compound when combined with the sulfate ion. All right, well, that's kind of interesting. The sulfate ion, if you didn't know, you would look at reference table E, but sulfate is SO42 minus, which is here on the table. But anything that is going to combine with sulfate is going to have a positive charge, not a negative. So sulfate is not combining with itself, nor is it going to combine with hydrogen carbonate, which is another negative poly. That leaves us with calcium ions, magnesium, and sodium ions. Let's go to reference table F and we'll figure this out. Okay, reference table F. We're looking for calcium, magnesium, sodium as it pertains to sulfate. Sulfate here, most of the time sulfate compounds are soluble in water except for these ions here. And for sodium, magnesium, calcium, the exception calcium means that calcium sulfate is insoluble in water. That's our answer. Just a reminder also, please, if you're writing down an ion, remember the charges go with an ion. Don't just put down calcium as the answer for 5. It would have been calcium 2 plus or plus 2. Number 6, numerical setup again. So we're just going to plug the numbers into the formula for calculating the parts per million of sodium ions in the 500-gram sample of the bottled water. Parts per million is on reference table T. Let's check it out, and we'll come on back and do the setup. All right, we're at reference table T. We're looking for parts per million, and here it is. The fraction, the mass of the solute over the mass of the solution. Remember that your solution is the whole thing. It's the solute plus the solvent. And we don't forget you're going to times by 1,000,000. You have to add that also, or else it's not going to be a proper setup. All right, so you're looking at the proper setup for number 6. Your mass of your sodium ions, your 0.0033 divided by the mass of the sample. That's the sodium ions plus the water times 1,000,000. Don't forget the 1,000,000, otherwise you're going to get it marked wrong. You don't have to calculate the answer, you just had to show the setup. One more question right now. Let's take a look. All right, in question 7, you're asked which formula can represent hydrogen ions in an aqueous solution. Well, I guess maybe I should have put this with acid-base chemistry, but again, we're dealing with polyatomic ions in reference table E. We use the fact that excess hydrogen ions in solution make an acidic solution, right? Low pH. But also water plus H plus is known as the hydronium ion, H3O plus. That's just H plus plus H2O, and that's our answer. The hydronium ion name is on reference table E, along with all these other polys, so hopefully you know where it is in case you need to take a look again. All right, we're moving on to reference table G and the solubility curves again. Now, we already saw one question, and here, down below table G, I have 2 more questions. In fact, this, I believe, was in a set, so I kept them together. More than likely, when you take the Regents, you're going to see a table G question also. Sometimes they will guide you to it, sometimes they won't. But realize if you're looking at how much of a certain solute dissolves in a given amount of water, check out table G. All right. In question 1, it says, based on table G, describe what happens to the solubility of SO2 gas as the temperature increases at standard pressure. Well, if we take a look at the solubility curves and we find SO2, what's happening as we go from 10 degrees to 30 degrees, it is going down, so it decreases. That's all you have to say. For this new question here, at 23 degrees Celsius, 85 grams of sodium nitrate are dissolved in 100 grams of water. I don't know exactly. Oh, okay. This shouldn't have been number 1. I didn't know exactly what I did. It's actually just a statement. The question is here, based on table G, determine the additional mass of sodium nitrate that must be dissolved to saturated at 23 degrees Celsius. All right, so we have 85 grams. We have to figure that's going to be below the line of saturation on the solubility curves for sodium nitrate. We got to go up to the line and then subtract. Let's go do that. All right, it's easier to do it here. I need to shrink this down in order to find it. Here is our sodium nitrate line, which is here, but of course you can't see the temperature at scale at the bottom. All right, let's take a look. This is a tough question to answer with my computer here, but 23 degrees is down here. I'm going to go up, and I want to cross the sodium nitrate line, that absolutely is right here, this slope, and then cut over. Oh, and sure enough, we're talking around 90 grams that will fit in 100 grams of water, right where the 23-degree line hits the sodium nitrate curve. So that's the maximum for saturation. Let's go back. All right, we said 90 grams in 100 grams of water at 23. We had 85 grams. We only need additional of 5 grams to saturate the solution. So that's the answer for number 3, which is really number 1, because these two should have been together. All right, question 2, convert the temperature of sodium nitrate to kelvins. You hear any growling in the background? That's 2 dachshunds that decided to wake up from their nap. All right, so 23 degrees Celsius. I'm going to change that into Kelvin. It's on reference table T. Let's go check out the formula. You don't want to make any mistakes here. Not only am I going to recommend that you go back always to find the reference table, here's the equation, and make sure you plug all the numbers into the calculator. 23 plus 273 is going to give us Kelvin, which is 296. Okay, so here we are at the vapor pressure diagrams, table H. Determine the vapor pressure of water at 69 degrees Celsius. We already did a vapor pressure diagram question above. This is the second, so 2 out of 3 on the most current Regents exams. Now, 69 degrees Celsius, well, the y-axis, it goes up by 5s. So 55, 60, 65, 70, 75, 69 then is right about here, and we want to cross the water line, which the curve, it's the second from the bottom. I know you can't see it right now, but again, I didn't shrink it. All I want to do here is go all the way over, and on the y-axis, we're counting up by 10, so 10, 20, 30. So 30 kPa for the vapor pressure of water at 69 degrees. Reference table I. Reference table I gives us heat of reactions associated with just a subset of all the reactions, of course, that we know. The first set are your combustion, then we have heats of formation, then we have down below salts dissolving in water. Let's take a look at this question. I know it says number 2, it's really number 1. My numbering system, I guess, wasn't so great, but you're told to go to table I, and you're asked which equation represents a reaction with the greatest difference between the potential energy of the products and the potential energy of the reactants. In other words, which one is going to give us the highest value? Now, you'll notice for delta H, you have negative values and positive. The negative value just tells you that energy is going to be released as part of the reaction. A positive value, energy is going to be absorbed as part of the reaction. There's actually a footnote at the bottom of this table that reminds you of that. So what we're looking for here is numbers. Aluminum plus oxygen forming aluminum oxide. Again, do absolute value, we're looking for the biggest value. The formation of liquid water from hydrogen and oxygen, that's less, so still aluminum, number 1 is still winning. Number 2, not high enough. We have the combustion of propane. It's also releasing energy, but not as high as the formation of the aluminum oxide. And then finally, in number 4, you might recognize this as glucose, and that's a negative 2804. The winner is choice 1, the aluminum plus the oxygen forming aluminum oxide. I don't know why my computer's acting wacky, but it is. That's all we're doing, is looking for the highest value. They were all exothermic because of the negative signs. The second question that relates to reference table I, which I put as number 3, don't know why, says based on table I, which compound dissolved in water by an exothermic process? Exothermic means you're going to see it listed as a negative value. And again, as I just mentioned, that the negative value tells you that it's an exothermic reaction. We're looking for sodium chloride. Well, that, of course, is endothermic. It can't be number 1. Sodium hydroxide, well, that's a possibility because it's a negative value. Ammonium chloride is given as endothermic, positive again, and ammonium nitrate, or choice 4. So 3 of the 4 are positive. The only one that's negative is sodium hydroxide, meaning it's exothermic. Your answer then is choice 2. Reference table J, labeled as activity series. What you're seeing on the left is a list of metals. You see metals in order from the most active, meaning the most reactive, wants to lose electrons the most, versus the least active, which doesn't want to react, on the bottom. Right here, only a couple of elements up, you see H2. Any elements below H2, which is copper, silver, and gold, they do not react in an acid. Any ones higher do react in an acid. Also, this gives us, for single replacement reactions, if you have a metal higher on this side of the table that is an atom versus the ions, it will force the other reactant to give up. Wait, strike that. We can also compare metals to metals, metal atoms to metal ions. If I have lithium as an atom, so solid lithium, and I put it in a solution that contains strontium ions, it will react. It will not react the other way. In other words, for redox reactions or single replacement, whatever is the individual metal in the atomic form, that has to be higher on reference table J than whatever metal is in solution as an ion with a charge, and then the metal higher will replace the metal that's lower. The metal higher wants to lose its electrons more than the one below, and it will force the metal below to gain electrons. Nonmetals, this is the order in which nonmetals are reactive. Now, metals are your losers, nonmetals are your gainers. So fluorine wants to gain electrons more than chlorine, bromine, or iodine. So if I have F2 and let's say sodium chloride, so I have chloride ions, the fluorine will want to go to fluoride, and it will force the chloride ions to become Cl2. So reference table J, let's take a look at a couple of questions. Okay, so there is a question here that based on table J, which metal is more active than tin? Now, I think they picked tin because the symbol for tin is SN, so they're trying to throw off students. It's SN. But less active than zinc. Zinc is ZN. Remember, you can get all the symbols for all the elements on reference table S. Don't take shortcuts when it comes to the test, and don't take shortcuts when you're practicing either. All right, so if it is less active than zinc, it's going to be below here, and more active than tin, it's going to be above. So we're looking for one of these 4 elements as our choices, and there we have it, choice 2. For number 2, which equation represents a spontaneous reaction? This is what I was just trying to describe with just the plain reference table. If I have a spontaneous reaction, first of all, metal replaces metal, or non-metal replaces non-metal. Now, in number 1, calcium is here, and barium is higher. Barium wants to lose electrons more than calcium, but in reaction 1, it's already happened. This will not be spontaneous. So number 1 can't be our answer. For number 2, I have cobalt and zinc ions. Again, the zinc ions are higher than the cobalt, not our answer. Next one, I have iron and magnesium. Magnesium is higher. It's already in the ion form. It is not going to be number 3 either. The only one left is number 4. So let's take a look. We have manganese, Mn, and we have nickel, which is below and shown as an ion. This one is going to be spontaneous. This one, if I take a piece of magnesium and I put it in a solution with nickel ions, it's automatically going to react because manganese wants to lose its electrons more than nickel. So the answer is choice 4. All right, reference tables K, L, and not to be forgotten, M are all about the acid-base unit. L gives you common acids. Now, it's easy to spot an acid. Hydrogen is written first. Granted, the organic acids are a little dicey, but really not that bad. And not for nothing, if you're dealing with a name and the word acid is in it, it's an acid. Your bases, your common bases typically are metals and OH. The only one that's a little funky is ammonia. And you should have learned with the alternative theory known as Bronsted-Lowry theory, that's when ammonia behaves as if it's a base and will accept a hydrogen ion, also referred to sometimes as a proton. All right, let's take a look here. In question 1, all you're asked is which compound is an Arrhenius base. An Arrhenius base means metal and OH. There's only one choice here, and that has to be choice 3. The other 3 are acids. It's not only the only Arrhenius base, it's the only base in the choices. So choice 3 is it. If you get any question with an acid or a base or both, go to this page. Don't be silly. Don't do it off the top of your head. All right, same type of question in number 2. Or did I? Oh, no. Now it's which substance versus which compound. Remember, I took the most recent Regents exams, and there's pretty much a theme going on. It looks like for every reference table, 2 out of the 3 Regents exams refers to that particular table. Here again, they literally almost copied it word for word. 3 of these are acids. The only base, and yes, it's an Arrhenius base, is the calcium hydroxide, or CaOH2. Let's check out some indicator questions. All right, in question 3 here, state the color of methyl orange in a sample of normal rainwater. Now, I wrote this in parentheses. It was from a reading passage. The pH was 5.6. Anything that has to do with acid-base indicators, and it has some of these funky names like methyl orange, brome cresol green, brome thymol blue, go to reference table M. All right, I'm dealing with methyl orange. I'm dealing with 5.6. When you're dealing with the colors and the pH, think of the pH as a number line. Anything 3.1 or lower is going to be red. Anything higher than 4.4 is going to be yellow, and then anything in between in this color change, red and yellow, make orange. Well, if I'm at 5.6, I think we'd all agree we're higher than 4.4, and the color is going to be yellow for number 3. For number 4, we're asked the color of brome cresol green with a pH value of 2. So now I go to brome cresol green. Here it is. Again, every single one of these has a transition, and then what it's changing from what color to what color. You need to know the in-betweeners, right? Red and yellow make orange. Yellow and blue make green. Colorless and pink makes a light pink. Red and blue, purple. Yellow, blue, you're going to have green in between, and thymol blue, you're going to have green in between. Well, 2.0 with brome cresol green, and we're going to be below the 3.8, which makes, again, the color here yellow, which is choice 4. Well, hold on now. We have another indicator question. Here I listed as number 6. That makes, for the past, most recent Regents Chem exams, 3 out of 3 with an indicator question. Okay, we're going to go to 6 and then back to 5. You have a reading passage. Don't forget about that. I added these bonus questions in here. 6 is asking about the color of brome cresol green if it is added to a sample of potassium hydroxide. Now, you need to know that potassium hydroxide is a base. Of course, you can go to the the common bases and find that it's a base because it's a metal in OH. Typically, bases are going to have high pHs. And if it's added to the sample, let's go back and take a look. HCl started with a value of 2. It's used to determine the molarity of KOH. Blah, blah, blah. Oh, exactly neutralized. So way it's reading, it says if it's added to a sample of the KOH. Well, let's take a look at brome cresol green. Brome cresol green, whether it's neutral at a pH of 7 or greater, is going to be the color blue. So your answer for number 6 would have been blue. Let's go back to number 5. Determine the pH value of a solution that is 10 times less acidic than HCl. Well, you're told that the HCl solution has a pH value of 2. Remember, as the pH number drops by 1, so if we were going to go from 2 to 1, the acidity of the solution would be 10 times greater. In this case, we want 10 times less. What that means is we're going to go from 2 to 3. Remember, as the pH value gets higher, the hydrogen ion concentration in my acid drops by a factor of 10 each time. So the answer to number 5 was 3. All right, question 7. Oh, I just lost it. I just tried drawing it. I'm having a tough time with my computer here and drawing things on the screen. You're asked to complete the equation in your answer booklet by writing the formula for each product. Well, what do we have? We have HCl, our acid, plus KOH. We say that acids and bases neutralize one another. I don't know why it keeps doing it this way. And it is a double replacement reaction. The only other type of double replacement reaction would be the formation of a precipitate. Okay, so HCl and KOH, acids split here, get the hydrogen ions, bases split also, you get the hydroxide ions, double replacement. You start with 2 compounds, you end with 2. Now, as far as the salt, it's just going to be K. Maybe not. Shouldn't be that hard. KCl and H2O. And I apologize. I got to figure out. It's been so long since I made one of these videos. I don't know if I use my Chromebook. I don't know what I use, but it should be KCl plus H2O. All right. Well, that was exhausting. Let's go on to number 8. Once again, we're showing a numerical setup here for the molarity of the KOH solution. Molarity has to do with the number of moles per liter. Let's take a look first at the information above. Remember, we had the HCl and the KOH that was put into the HCl to exactly neutralize each other. So when they're neutralizing one another, that's where in the last question, we got the salt and the water. So we need an equation. Let's go to reference table. All right, so we're looking for the neutralization equation. Well, it isn't called that. It's actually called the titration equation, because when I exactly neutralize an acid and a base, I'm going to have equal moles of both. So I'm going to use this equation for figuring out the answer. Okay, so here it is. I have my molarity times my volume of A, meaning acid, my molarity times volume for B, meaning my base. From above, I have a 0.1 molar hydrochloric acid solution. I have 15 mils. So 15 times 0.1 on one side. On the other side, I don't know the molarity, so that is my X, and 7.5 is my volume. Now it asks for the numerical setup, so once again, you're going to go ahead and have the setup, and you're done. Please make sure. You don't even have to put units in, but you have one side equal to the other. Please don't forget the equal signs. Let's keep going. All right, we're going to stop here. We're going to call this the Mega Regents Chem Reference Table Review Part 1. We've gone through of the 20 tables. Actually, A through J would have been the first 10. We added a couple more, the K, the L, and the M. So we have the last 7 to go through. And of course, the periodic table. We'll do that in the next video. Keep working hard. Good luck. Obviously, there are questions that involve the reference tables, and you see a decent sprinkling of all of the reference tables being used. The more that you do, the more that you can prepare for this test, the better off you're going to be. Check out my other videos on my YouTube channel, and good luck.